Section 4.6 Optimization Problems. The methods we have learned in this chapter for finding extreme values have practical applications in many areas of life. A business person wants to minimize costs and maximize profits. A traveler wants to minimize transportation time. Fermat's principle in optics states that light follows the path that takes the least time. In this section and the next, we solve such problems as maximizing areas, volumes, and profits, and minimizing distances, times, and costs. In solving such practical problems, the greatest challenge is often to convert the word problem into a mathematical optimization problem by setting up the function that is to be maximized or minimized. Let's recall the problem-solving principles discussed and adapt them to this situation. Steps in solving optimization problems. Number 1, you want to understand the problem. The first step is to read the problem carefully until it is clearly understood. Ask yourself, what is the unknown? What are the given quantities? And what are the given conditions? Number 2, draw a diagram. In most problems, it is useful to draw a diagram and identify the given and required quantities on the diagram. Number 2, introduce notation. Assign a symbol to the quantity that is to be maximized or minimized. Let's call it Q for now. Also select symbols for other unknown quantities and label the diagram with these symbols. It may help to use initials as suggestive symbols, so for example, A for area, H for height, T for time. Number 4, express Q in terms of some of the other symbols from step 3. Step 5, if Q has been expressed as a function of more than one variable in step 4, use the given information to find relationships in the form of equations among these variables. Then use these equations to eliminate all but one of the variables in the expression for Q. Thus, Q will be expressed as a function of one variable x, say Q is equal to f of x, and then write the domain of this function. And number 6, use the methods of section 4.2 and 4.3 to find the absolute maximum or minimum value of f. In particular, if the domain of f is a closed interval, then a closed interval method in section 4.2 can be used.